Hey everybody. Okay, time for the next chapter. So what we're going to be looking at today is restarting organic chemistry. Don't be frightened, just means carbon. So we're going to start with some of the simplest organic molecules. Alkanes and halogenated hydrocarbons. Now you should know what halogenated means. You know what a halogen is. It just means that one of the halogens is covalently linked to our hydrocarbon, and we're going to learn how to name them, different ways to draw them, and get to know some of their how they're composed, uh, what they do in as far as chemical reactions go, and some of their chemical properties. So we're going to learn to recognize the difference between organic and inorganic compounds. We're going to identify and name straight chain alkanes, and we'll talk about the difference between straight chain and branched alkanes. Be able to name them using the international system and write formulas based on those IUPAC or international system names. And we'll learn that some alkanes can actually be ringed, and we call those cycloalkanes. And we'll be able to name and draw those as well. So as I mentioned, organic, don't be frightened of organic. It just means carbon-containing molecules. And of course, there are just, billions of carbon-containing molecules all around you, inside you. And so, when you go to the grocery store, there's a sort of a meaning of the word organic. Basically, organic at the grocery store means it wasn't grown in the presence of pesticides or herbicides or that sort of thing, things that kill bugs and different things that can harm fruit. But chemist, when he hears the word organic, or she hears the word organic, just thinks, oh, carbon-containing molecule. And carbon is essential for life. And here are some of the inventions that we're sort of familiar with as far as organic goes. Penicillins were discovered in the early part of the 20th century. These are molecules that are naturally made by fungus, and they kill bacteria. And so this, for the longest time, was the only antibacterial drug that we had. And now we've been able to make a whole bunch of changes to this particular molecule and make it a little more functional. Make it so that even penicillin-resistant bacteria will be killed by small changes to this particular molecule. Plastics, of course. Everyone's familiar with plastic. But really, plastics didn't really come along, again, until about the 30s and 40s. And these are long synthetic chains. And you can see from this particular molecule, it's a polymer of an alkane. And so now we make, millions of tons of plastic. We probably shouldn't make quite so many. Really interesting here is this was the very first, the pill, the very first contraceptive pill developed in the 50s, I believe. And this particular molecule was found in yams, and a synthetic organic chemist was able to just do a couple of small changes and turn it into progesterone, the naturally occurring hormone in women involved in reproduction. And this particular ring system right here actually comes from cholesterol. Cholesterol is actually converted into a whole bunch of different molecules inside your body. In fact, interestingly, it's the cholesterol part of this molecule that's actually turned into testosterone as well. And so testosterone, estradiol, a lot of the sort of sex hormones are produced from the same core, which is cholesterol. And then finally, liquid crystal displays. This was an organic molecule discovered in the 70s and shown that it could broadcast electricity, could move electricity in a particular way that caused particular colors to be established. And this ring right here, we're going to learn a lot more about. That's an organic ring called benzene. What's interesting about that particular molecule, we call that an aromatic ring. And we're going to learn more about that in the next chapter. So, study of chemistry of carbon compounds. Carbon is really interesting in terms of its chemistry because it's sort of right in the middle of the non-metals. And carbon atoms make pretty strong bonds with other carbon atoms and bonds reasonably strongly with other atoms of other elements as well. And we know that since it's in group 4, it makes 4 covalent bonds. And since carbon atoms have only slightly higher than average electronegativity, they're able to make nonpolar bonds with hydrogen and polar bonds with oxygen, nitrogen, and all of the other halogens like fluorine, chlorine, etc. So carbon atoms can make polar bonds, they can make nonpolar bonds, they can make aromatic bonds, and we'll learn more about them. They can make double bonds, they can make triple bonds. So carbon atoms are really, really versatile in their chemistry, which is why we devote an entire portion of chemistry to just the chemistry of carbon. Now, we know that most organic chemicals are covalent, and all living things consist of organic compounds. You, me, your cat, everything else. Now, the simplest, we're going to start at the beginning, and the very simplest organic compounds are called hydrocarbons. And you can pretty much figure out what 2 elements are involved in that. Hydro for hydrogen and carbon for carbon. So they only are composed, the simplest ones are only composed of hydrogen and carbon. So we call them hydrocarbons. And then there's a number of different kinds. We have alkanes, which you probably have heard before. Alkane are what's called a saturated hydrocarbon. That's an important thing to remember. Saturated. Saturated means that only single covalent bonds between carbons are present. So there's only single bonds between all the carbons in that particular molecule. And so we say that since there's only single bonds in the entire molecule, that it's completely saturated. We can't add any other compounds to it without breaking single bonds. An alkene has a carbon-carbon double bond in it. Now, there's a lot of reactions we can do with this particular molecule. Since it has a double bond, we can break one of these bonds and then add something to it. We could break one of the bonds and add a pair of bromines to it or something like that by breaking one of those bonds. We could add hydrogens to it. We could add a number of different elements. But since there's at least one double bond, we call it an alkene with an E rather than an alkane. And then finally, there's alkynes with the Y. That refers to a compound that has at least one triple bond between carbons. One of the simplest ones is something you may have heard of. That is the gas used for welding. That is acetylene. That's the simplest alkene with one triple bond between carbons and then hydrogens on the end. It's used for welding because it takes a lot of energy to break this triple bond in the middle. And so it burns at a very high temperature. And you can melt things like steel with it because it burns at such a high temperature. So now we're going to look at ways to draw these different structures. There's a lot of different ways to depict hydrocarbons. We're going to learn some of them now. One of them is called a condensed structural formula. So this would be the molecular formula here. That's like the simplest way. That's just the formula for the molecule. So just looking at that, we can see that it's got 3 carbons and 8 hydrogens. But we don't really know how they're arranged. So we have a condensed structure, which basically shows us each carbon and how many hydrogens they're bonded to. So from this, we can see that the first carbon has 3 hydrogens attached to it. The second one is attached to one of the carbons on one side and one of the carbons on the other side, and 2 hydrogens. And the third one is bonded to the carbon in the middle and 3 hydrogens. So we can see that each one of those carbons makes 4 bonds. And there's really no more places for extra things to be attached. This would be an alkane. Because when we draw the Lewis structure, we can see that each carbon is making 4 single bonds. So 1, 2, 3. We can see that each one of them is making 4 single bonds. That's an alkane. Okay? Let's draw the condensed structural formula for these 2 Lewis structures. First, we sort of see how many carbons we have. So A, we've got 1, 2, 3, 4, 5. So remember, for the condensed formula, you basically draw each carbon and how many hydrogens is attached to it. And this is an alkane, so there's not going to be any double bonds. So the first one is a CH3. Second one is a CH2. Third one is a CH2. Fourth one is a CH2. And the last one is a CH3. So that would be the condensed structural formula for A. 1, 2, 3, 4, 5 carbons, and each of them having single bonds and attached to the maximum number of hydrogens. Second one is a lot easier. We just have 1, 2 carbons, and they're each attached to 3 hydrogens. So CH3, CH3. Now let's draw Lewis structures for the condensed structure. So for the first one, we've got 1, 2, 3, 4 carbons, and they're each attached to the maximum number of hydrogens that they can be attached to. So we'll just go 1, 2, 3, 4, and then each one of them is attached to the maximum number of hydrogens. So there we go. That would be the Lewis structure for that one. Now B, we can see that there's a double bond in there between carbon number 2 and carbon number 3. So for that one, we've got 1, 2, 3, 4, 5, 6, 7, 8 carbons. So we go 1, 2, and then notice that we've got a double bond between 2 and 3. And then a single, a single, a single, a single. Is that 8? 1, 2, 3, 4, 5, 6, 7. Oop, one more. Didn't leave myself room for it. Carbon there. So then we just put the hydrogens on. Now remember, each carbon can make 4 bonds. So this hydrogen, 1, 2, 3 on that particular carbon. Now the second carbon already has 3 bonds, so it only has room for 1. Same is true of the third carbon. It's making 3 bonds already, so it only has room for 1. And then the rest of them have the usual number of hydrogens. The last one would have 3. So that'd be the Lewis structure for the second one. So look and see where the double bonds, where the triple bonds are. And remember that each carbon makes 4. So if a carbon is making a triple bond with another carbon, and it's in a long chain, these 2 carbons here are already making 4 bonds, the triple and then the single bond on either side. So there's really no room for hydrogen on either one of those. Carbons in a long chain with a double bond have 1 bond left over, and so they can be bonded with 1 hydrogen. And carbons that are making all single bonds in a long chain have a carbon on one side and a carbon on the other side for 2 bonds, and they have room for 1, 2 other bonds for hydrogen or whatever else. Now the other way that organic chemists generally draw these molecules is what we call skeletal structures. Now this is what we call sort of a bare bones skeletal. Yeah, you get it. Because it basically only shows bonds between carbons or other non-hydrogen elements. So, and then the carbons aren't even drawn. They're basically just shown as lines. So for instance, this would have 1, 2, 3, 4, 5 carbons. And we would just assume that everything else, since there's no double bonds here, these are just single lines, we would just assume that everything else was hydrogens because we don't draw in the hydrogens. We just assume they're there. Now this molecule over here is naproxen. It's the active ingredient in Aleve, as you can see. One of the really strong non-steroidal anti-inflammatory drugs like aspirin and acetaminophen. So when you're drawing that particular molecule, notice that anything that isn't hydrogen is shown. So here we can see there's an oxygen in the middle. So there's a carbon-oxygen bond. Over here, we can see an OH or a hydroxyl group. So that's attached to a carbon. It has 2 organic rings in the middle. And when you have a branch like this, a small branch like that is a single carbon coming off. So this branch here would be CH3, or what we call a methyl group. CH4 is methane, so if it's bonded to another carbon, we take one of the hydrogens away because it's got a carbon-carbon bond, and we call it a methyl group, YL. We'll learn about that in a minute. So just bonds to carbons and other things other than hydrogen. So here we have the very simplest molecular formula. Here we have the condensed formula, which shows you each carbon and who it's bonded to. And of course, we're familiar with the Lewis structure, which shows you every bond in a molecule. This would be the skeletal structure, just 1, 2, 3. So from here we know there's 1, 2, 3 carbons, and since there's nothing else shown, we know that A, it's saturated because they're all single bonds, and B, there's nothing else but hydrogens. So we just assume that there's 3 hydrogens there because that carbon is only forming one other bond. We know that this carbon at the end is also bonded to 3 hydrogens because it's only making one other bond. And this carbon in the middle has 2 hydrogens attached because it's making 2 other bonds for a total of 4. And then from that, this would be what we consider a ball and stick model. We're like when you make representations of molecules using these model building balls and sticks, that's actually what the molecule would look like with all the proper angles and everything else in it. So you can see that from this, you can sort of see that tetrahedral arrangement of the bonds, right? You can see the tetrahedral arrangement. So each carbon is in a tetrahedral shape because we know that carbon making 4 bonds is a tetrahedral shape. We learned that already. So these are the rules. We show the carbon-carbon bonds. We don't show the carbon-hydrogen bonds, but we know they're there. And then other elements bonded are shown with their symbol. So like if there's a nitrogen in there, a sulfur in there, an oxygen, basically anything but carbon or hydrogen. Lone pairs are not shown. So lone pairs we assume to be there. So if we have something like carbon, nitrogen, carbon, we know that nitrogen makes 3 bonds and has a lone pair. So we would assume from that we make a hydrogen and have a lone pair. So that is just assumed, okay? So we determine the number of carbons. We look at the molecule, count the number of carbons there are in a row, draw the bonds between them. That's the skeleton. And then we draw bonds to whatever non-carbon atoms there are. So the first one, 1, 2, 3, 4. This is the skeletal structure with just the carbons, and there's nothing else other than hydrogen there. So we're done. We just leave it. Now the second one, we have 1, 2, 3. So we go 1, 2. Oop. Sort of done with that one. We go 1, 2, 3, and we can see that there is an OH group, a hydroxyl group. So we just put an OH there. And everything else is a hydrogen, so we just leave it. Okay? Now, here's an example. We'll do some more examples on Tuesday. We're just going to have a look at some of these now. So for the first one, we see how many carbons there are in a row. And so there's 1, 2, 3, 4, 5. So there's 5 carbons. So I would just go 1, 2, 3, 4, 5. And the first one is only making 1 bond with another carbon, so we can assume it's got 1, 2, 3 hydrogens. Now the second one we can see has a chlorine atom, and it's bonded to 2 other carbons, so it's got bonds with 2 carbons and a chlorine. Well, it makes 4, so we can assume that the other one is hydrogen. So here's our chlorine would go there, hydrogen would go there. Number 3 also has a chlorine. So we would put a chlorine there, and it's bound to a hydrogen. The fourth one and the fifth one are only bonded to carbons. So hydrogen there, and the third one would have 3 hydrogens. So that would be the Lewis structure for the first one. Now for the second one, let's see what's the longest stretch of carbons. So 1, 2, 3, 4. So if we went that way, there's 4. But if we go straight along, there's 1, 2, 3, 4, 5. So that would be the longest chain in a row. So we go 1, 2, 3, 4, 5. So the first one, and they're all bonded to each other. First one just has hydrogens. Second one just has hydrogens. The third one has a methyl group, CH3 is called a methyl group. So we would put it up here, 1, 2, 3, and a hydrogen down there. The fourth one just has hydrogens. So a hydrogen there and a hydrogen there. And then the last one on the end has 2 hydrogens and a bromine. So hydrogen, hydrogen, bromine. Okay. So let's look at alkanes in general. Now remember, alkanes are the simplest compounds. They have only single bonded carbon and hydrogen. Well, hydrogen is always going to be single bonded because it's only got the 1 electron. So we typically refer to them as saturated hydrocarbons because they're all single bonds. There's no double bonds in an alkane. Only single bonds. So each carbon atom is bonded to the maximum number of hydrogen atoms. So carbons on the end are bonded to 3 hydrogens, and carbons in the middle of the chain are bonded to 2 hydrogens. So that's the maximum number of hydrogens that carbons at the end and carbons in the middle can bond to. So straight chains, there's a number of different ways that alkanes can be organized. So we have ones that just have carbons in just a straight chain going like that. So they are continuous unbranched chains. Now these things can also, as we'll see in a minute, can be branched. You can put together carbons in all kinds of different ways. And each compound is given a name based on the number of carbon atoms in the chain. And you're probably familiar with some of them, like propane has 1, 2, 3 carbons in a row, and that's what you use for running your gas-fired barbecue. The simplest one, with just just 1 carbon, is methane. We've seen that before. And then ethane, propane, butane, like you would see in a small lighter, and then pentane, hexane, heptane, 2, 3, 4, 5, 6, 7, all the way up to 10. Decane. And this is what we call a homologous series because each one follows by a definite factor. That definite factor, an additional saturated carbon. So we had 1, we had 2, we had 3, we had 4. So we're continuously adding 1 additional saturated carbon. So we call this a homologous series. And you can always tell the formula for an alkane by looking at the number of carbons versus the number of hydrogens. So because each interior carbon can be bonded to 2 hydrogens, and the ones on the exterior can be bonded to 3, then we can tell immediately how many hydrogens should be in a saturated alkane. We count the number of carbons and we multiply by 2. These would be all the interior carbons. And then to make up for the carbons on the outside, we know they can bond to an additional 2 hydrogens, or additional 1 hydrogen, and there's 2 at each end. So the formula is C to the n, whatever n is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The number of hydrogens will be twice that number plus 2. And the plus 2 is the CH3 on one end and the CH3 on the other. That's an additional hydrogen on each end. That's where you get the plus 2. So just see how each one of these, just take any one of them, like heptane, for instance. It's got 7 carbons. You can instantly calculate how many hydrogens it should have. 7 times 2 is 14, plus 2 is 16. Yep. Now, because of that, we can look at the formula and we can tell whether it's an alkene, an alkyne, or an alkane, depending on how many hydrogens are there. Because with an alkene, we take away 2 of the hydrogens because we have a double bond. With an alkane, we take away 4 hydrogens because there's a triple bond. So we're taking away places for hydrogen to bond when carbon bonds with each other. Now, alkanes can also ring together. Instead of having ends, they can come together and attach themselves. So we can form rings of 3 is the smallest, of course. And we would call that cyclopropane because they're propane, pro meaning 3, ane meaning it's an alkane, and cyclo meaning it's joined together. 5 and 6 carbon rings are most common. You're not really going to see a lot of cyclopropane because there's not a lot of room for those 3 carbons. When you join them together, there's going to be a lot of strain in those bonds because they're basically too close together. And so something like cyclopropane would just, there's a lot of energy in those bonds waiting to break. It's much more stable when you have 5 or 6 atoms and you get more room for the carbons to make the proper shape, because we know that carbons making 4 bonds like to have that tetrahedral shape, and when you force them into a shape where they can't basically make those, then you get a lot of strain and those bonds tend to break. So here's some of the cycloalkanes, and you can see that when you're drawing those, you're basically just drawing the shape they make. So if there's 3, you're drawing a triangle. If there's 4, you're drawing a square. If there are 5, you're drawing a pentagram, and then you're drawing a hexagram. And notice that we can tell if they're cyclo because now we don't have any terminal carbons. Every carbon in the molecule is bound to another carbon. And so the formula is now different. It's now C to the N, H to the 2N, because we don't have any terminal carbons making a CH3. They're all making CH2. And so the formula is going to be different. So remember, alkanes are super nonpolar because carbon-carbon bonds are nonpolar, right? They're extremely nonpolar because you have the same electronegativity on either side. Carbon-hydrogen bonds are also nonpolar. The difference in electronegativity is less than 0.4. It's actually less than 0.3, so it's really nonpolar. So regardless of their shape, all alkanes are nonpolar. And so the nonpolar of these alkanes affects what they do when you put them in water. Water is helipolar, right? So if you put these compounds in water, they do not dissolve. They will separate themselves. If you take gasoline, which has a lot of straight chain alkanes and octane and heptane and all these other ones, and put water in it, the water just sinks right to the bottom because they don't have any ways of interacting with themselves other than London dispersion forces, which are the very weakest. Water would much rather hydrogen bond. So if water can hydrogen bond with itself, it's going to do that. And the organic molecules, the non-polar ones, are just going to make London dispersion force interactions with each other. And so they'll be completely separate from each other. So we know that these are used for combustion. You're putting them in your fuel tank every day. Mostly, like I said, mostly octane, but there's a whole lot of other molecules in there too. Like in biodiesel, you have these long chains with some oxygens in them, which help them burn a little bit better. Now, when you completely combust these, like cleanly, you only get CO2 and water. But anyone who's had their car smogged know there's a lot of other molecules that are produced in a car engine because it's not perfect combustion. There's nitrogen in there. We get nitric oxides. We get incomplete combustion, and so that's one of the things that's tested for when you take your car in to get smogged. If there are hydrocarbons, if you look at the report, one of the things they look for is HC, and that is unburned hydrocarbons, and you can smell those like when you're driving down the street. Some car has not been tuned in quite a long while, and it gets what's called a too rich a mixture, meaning there's too much hydrocarbon for oxygen, and so not all the hydrocarbons get burned, and some of them get shot through the tailpipe, and you can smell them. It smells like gas, and not pleasant to drive behind them. So let's see how we name these. So if we have a saturated hydrocarbon, we want to look and see what's the longest continuous chain of carbons. And that's what we'll use to name the molecule. What chain of carbons is the longest continuous one in the molecule? So organic compounds that have at least one carbon-carbon double or a carbon-carbon triple bond, we call those unsaturated. You've probably heard of unsaturated fats, right? Well, unsaturated fats have triple and double bonds in them. And what makes them, that's why they're unsaturated. So that turns them basically into oils rather than solids. And it's because these double and triple bonds make bends or kinks in these long molecules. And with these bends and kinks in it, it prevents them from easily forming large London dispersion forces among similar long compounds, similar long hydrocarbon tails. When you have the long hydrocarbon tails, you get saturated fats where all of the carbon bonds are singles, and they tend to all have the same shape and then line up on top of each other and form solids at room temperature, like margarine, for instance. So alkenes, remember, have double bonds. Alkynes have triple bonds, and we'll talk about aromatics. Aromatics have rings with alternating double and single bonds that have very special chemical properties that we'll talk a little bit about next chapter. So how do we call these things? Well, we look for the number of carbons in the longest chain. We look and see if it has any substituents, any attachments, any other things attached to it. And then what family is that? Is it butane? Is it octane? Is it heptane? What is it? So we look and see which is the longest one, whether there's any branches in it. For instance, is there a methyl group sticking out? Is there an ethyl group sticking out? Ethyl would have 2 carbons. And so we look for those, and then that's how we decide their name. So let's start with this molecule here. Now, which has the longest branch, longest single going across from one to the other? Well, we can see that there's 1, 2, 3 in this direction, and there's also 1, 2, 3 in this direction. And in fact, if we were to make a model of this, we would see that those two are exactly the same molecule. Just a matter of which orientation they're in. So the longest one is 3. So C3. Then we would look and see, are they all hydrogens? Well, the first one is all hydrogens. The last one is all hydrogens, but the second one has CH3 attached to the second carbon. That is a methyl group. So that name comes from the alkane, methane, ethane, butane, and we substitute ane for the YL. So that becomes a methyl group. So the name of this would be, name what the substituent is. It's methyl. Where is it? Which carbon is it attached to? 1, 2, 3. Notice that it doesn't matter which direction you go into. If I went 1, 2, 3, or 1, 2, 3, it doesn't matter which direction I go into. That methyl group is attached to carbon number 2. So we have to say where the substitution is. Where's the substituent? It's at position 2. What is the substituent? It's a methyl group. And what is the longest continuous chain of carbon molecules? 3. Methane, ethane, propane. Propane. So propane. So that would be 2-methyl propane, meaning it has 3 carbons in a row, and on the second one, instead of a hydrogen, it has a methyl group. So these are what we call the different substituents. So methyl, just a carbon with 3 hydrogens. For methane, ethyl has 2 carbons, and instead of ethane, it's ethyl. So it's attached to a carbon here, carbon-carbon bond. Propyl, meaning 3. Now propyl means 3 carbons in a row, 1, 2, 3. Isopropyl, and you've probably heard of isopropyl alcohol or rubbing alcohol, that is a branched. So instead of having 3 carbons in a row, we get 1 and then a carbon on each side. So we still have the 3 carbons for propyl, but instead of it going 1, 2, 3, it goes 1, 2, 3. So this hydrogen this carbon in the middle only has 1 hydrogen attached. So rather than it being a straight chain, it's branched. That's where the iso comes from, because it's an isoform or an isomer of. An isomer just meaning the same molecule but a different shape. It has a different shape, and so we say isopropyl rather than propyl. All right, let's have a look at these. So first we look for the longest chain of carbons. So I have 1, 2, 3, and then 4. So 1, 2, 3, 4. That makes it butane. So whatever this is, it's butane. And then we look and see what the substituents are. So from the substituents, it has just a single carbon here, there's a single carbon on that one, and there's a single carbon on that one. So which carbons are they? Well, if I start here with 1, 2, 3, 4, we can see that this substituent is on carbon number dos, and this one is on carbon number 3. And you can see it doesn't matter either direction I went in, they would be carbon 2 and carbon 3. If I started at this end, it would be carbon 2 and 3, and if I started at this end, it would be carbon 2 or 3, so it doesn't really make any difference. So what are those substituents? Well, it's just a single line, so that means it's just a carbon, and remember, we assume that it's saturated, sorry, so that would be carbon with 3 hydrogens attached to it, so that would be a methyl group. So that would be 2, 3, dimethyl, di for 2, 1, 2, 3, 4, butane. Now let's look at the second one. A lot going on in this one. So what's the longest stretch of carbons? So I got 1, 2, 3. Now if I go down this way, it's 5. If I go the other way, it's 5. So, number of ways I could go with this one. So if I go this way, that's 5. And if I go the other way, it's also 5. So what I will do is basically see which one gives me the lowest number of substituents. And if I go this way, then I've got 1, 2 substituents. If I go the other way, if I go 1, 2, 3, 4, 5, then I've got a substituent with a substituent on it. So that's going to make my life difficult. So what I will do is just go straight across. So 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. That is pentane. So whatever it is, it's pentane. So I number them so that the number of the substituents is lowest. So my first number would be smallest. So if I go in this direction, that would make this carbon 1, 2, 3, 4, 5. And so we can see that there is a substituent on number 2, which is a CH3. So that's methyl. And on number 3, there is a 2-carbon substituent. That is ethyl. C2H5 is ethyl. And so methyl is on carbon 2, ethyl is on carbon 3. So that would be 2 methyl, 3 ethyl pentane. Okay? We'll do more of these on Tuesday. So the simplest of these molecules, the alkanes, can have other substituents, of course, not just other carbon substituents. They commonly have halides from halogens attached. So what does that mean? That means fluorine, chlorine, bromine, iodine. And so we call those fluoro, chloro, bromo, or iodo. And so the rules for those are just the same as the others. So we would say, 2-fluoropentane or 3-chlorohexane, for instance, rather than methyl or ethyl. And we just say where is the halogen? Which carbon is it attached to? So when we get to cycloalkanes, the rules are slightly different. The ring serves as the parent name this time. So instead of saying hexane, we would say cyclohexane. Instead of pentane, we would say cyclopentane. Number the carbons in the ring, 1 to whatever. If there's only one substituent, that's what we call carbon 1. Because remember, we want to use the lowest number possible when we're naming them. So if there's only one substituent, that automatically becomes carbon 1. If there's two substituents, we name one of them 1 and the second one 2, going in alphabetical order. So we assign numbers to the substituents. So if there's only one, we don't need to say which carbon it's on. We assume it's on carbon 1. So if we have, let's say, 1, 2, 3, 4, 5, 6, so I've got hexane and there's a single chlorine on it, I would just call that chlorohexane, and with the assumption that that's carbon 1, although it doesn't really matter because there's just one substituent. If there's two, then we would have to worry about what's the alphabetical order of chloro, bromo, iodo, whatever. And we always want the lowest possible combination of numbers. We want to have 2 and 3 rather than 5 and 6, for instance. We want the lowest numbers we can possibly have. So let's look at these two. So let's see what our longest carbon length is for A. So I got 1, 2, 3, and then if I went this way, it would be 4. But if I go the other way, there's 4, 5. So 1, 2, 3, 4, 5. So that's pentane. So I know I've got a pentane. And then which order do I go in? Do I start naming this one with 1, or do I start with this one as 1? Well, I can see that if I start this end as 1, then I have a chlorine substitution at position 2. If I go the other way, I would have this substituent at 1, 2, 3, and chlorine at 4. So I would have 3, 4 rather than 2, 3. And I want low numbers. So 2 and 3 are the way to go. So it'd be 1, 2, 3, 4, 5. That'd be the direction I would name them. So I know I have pentane. 1 is saturated, so that's CH3. 2 has a chlorine, so we call that chloro. That would be 2-chloro. And then where's my next substitution? It's right on the third one, so 3. And what is it? It's just a single line. Lines, remember, mean carbon-carbon bonds. So it's a single carbon. That would be methyl. That is a methyl group, so 3-methyl. That's nice and neat. So 2-chloro, 3-methyl pentane would be the name of that one. Now B, much easier. So B, I've got a circle, not a circle, but they're all connected together. So that's a cyclo. How many in it? 1, 2, 3, 4, 5. So that's cyclo. 5 is, quickly, hexane, no, that's 6. Butane, no, that's 4. What's in between? Pentane again. So, cyclopentane. And it's only got the one substituent right there. So it's a methyl group. And so we just call it methyl cyclopentane. We don't have to say 1 because that's assumed. If there was another substituent, we would call that 1, and then say that there was a substituent here at there's a chlorine there at 2, we would say 1-methyl-2-chlorocyclopentane. But if there's only one, you know it's at position 1, so we just say methylcyclopentane. Okay, so we're going to do a lot more of these on Tuesday, and I'll be posting the workshop this afternoon. So any questions, let me know. I will see you on Tuesday, and we'll go over a lot of this again. All right, talk to you soon.